Okay, hello class. In this lesson we're going to learn how to solve polynomials. We've already actually talked about a lot of these ideas, but we're going to look at them in kind of a deeper way. We're going to factor and solve polynomial equations. We're going to use the rational root theorem as a way of factoring, and then we're going to use irrational conjugate theorem to find other factors. Number one idea, whenever we solve polynomial equations, the method we're going to use is factoring. With quadratics, we had a number of different ways, but with polynomial equations specifically, we're always going to factor. So here's an example right here where we have this polynomial equation. First thing we do is we attempt to make one side 0. That is the key thing before we factor. Then we factor this down, and this is in a quadratic form, so it kind of drops down to this, drops down to x plus 3x minus 3, and another x plus 3x minus 3. And we see here that our solutions, using the zero product property, setting any one of these to 0, we get solutions at -3 and 3, and then some repeated ones again at -3 and 3. And I just use this word repeated zeros because that's really what it is. We have this idea that there are two x plus 3 factors indicating a -3, 0. There's two of them, and so the terminology we say is that they're repeated. At x plus 3, they're also repeated, in this case, at x minus 3, or the x minus 3 factor is repeated, and the 0 at 3 is repeated twice. Now, over here we had this kind of interesting behavior where it kind of came down, touched the axis, and came back up again. We hadn't seen this before, and this is actually what it's called a zero behavior. Sometimes it crosses through, sometimes it just touches. In the case where we have a factor of x minus a to the nth power, if the power is even, like if it's squared, fourth, if we repeat this time an even number of times, it just touches the axis. Whereas if it's an odd power, like to the first power, and this is what we've seen a lot of in the past, it will actually cross through the x-axis at the 0 point. So here's an example. We have this polynomial, and we see that x minus 2 here corresponds to this 0 right here, and this x plus 1 corresponds to this 0 right at -1. In this case, right over here, it just touches the axis. It doesn't go through the axis because the exponent, the power, is to the second power, even number. When we have an odd number here, x minus 2 to the cubed, instead it actually crosses through that. A simple way I think of memorizing this, a simple way I think of memorizing this is if I have y equals x to the first power. This is the simplest of all kinds of graphs. We see a 0 at 0, and it's to the first power, and it crosses. Here's a second one, y is equal to x squared. Again, we have a 0 at 0, but in this case, instead of crossing through, it just touches right at the 0. So this is a very prime example. X squared, even, exponent, touches. X to the first power, odd, exponent right here, it crosses through. And if that helps you remember it, that's good. Okay, so here's a little example that you can give a try on. You could fill out the leading coefficient, the degree of the polynomial, the zero behavior, and I'll show the answer in 3, 2, 1. Okay, but sometimes it's hard to factor. And this is where the rational root theorem comes in. Sometimes the different methods that we have to use to factor don't work. So the rational root theorem is a way of creating all the different possible roots of a polynomial. So what it is saying is, if we have this polynomial where these are all integer coefficients, we know that the possible root will have a form p divided by q, where p is a factor of the constant term at the end, and q is a factor of the leading coefficient. Now, all this does is gives us a list of the possible roots. Bad thing is we need to actually check to see if they are roots, because we might find that none of them are roots. After going through checking all the possibilities, maybe nothing shows up. Now, here's an example. Now, we cannot group this. Since we have 4 terms, that would be something to give a try of, but it doesn't work. So we make a list of all the possible roots. And this is kind of my shorthand way of starting out doing it, where I say, okay, what are all the factors of 24, negative 24? I have plus or minus 1, 2, 3, etc., all the way to 24. My factors of 1, fortunately there's only one of those, because my leading coefficient is only a 1 here. Okay, so then I think of all the possibilities, plus or minus 1, plus or minus 2, plus or minus 3, etc. These are all the possible roots. Maybe none of them are roots, but we need to test them out now, one by one. So let's start testing it. We test out it by, one of the methods is just by plugging it in, plugging 1 into the function, and if it's equal to 0, then it's a root. Otherwise, it's not. And in the case of f of 1, no good, not a root. F of negative 1, no good, not 0, not a root. F of 2, no good, not a root. F of negative 2 equals 0, yes. Therefore, x is equal to negative 2 is a 0. Therefore, x plus 2 is a factor. Now, at this point, we divide and we factor it some more. So we take this, x plus 2 here, we put it into our synthetic division and run through, and we get 0 as we expect. And this leads to our quotient term that we're going to fill in right here. So we have x squared minus x minus 12. Now, let's see if we can factor this some more. Once we get down to a quadratic, we can use our other methods. We don't have to use this anymore. There's no need to go back and do this necessarily. We can just try to factor it kind of by our old methods. And in this case, x minus 4, x plus 3 is the factored version of this. Okay, let's look at one more example. Oh, we could graph this. We can graph each of the zeros, negative 2, 4, and negative 3, right there. Second step, we think about the end behavior. Here's the end behavior. It's odd degree, and it's a positive coefficient, so it's going to behave like a line, a positive slope line. So negative infinity over here, positive infinity over here. We could easily extract the y-intercept. If we plug in 0 here, 0 plus 0 plus 0 minus 24, that's minus 24. And then we can connect up the dots. Okay, and it's just a sketch. It's not a perfect graph, but it gives us a pretty good idea of its behavior. Okay, let's look at another one here. The difference here is that the leading coefficient is not 1, and so we have some a set of numbers in the denominator in this case. The numerator factors of 4. It's not too bad, not too many. But now as we list them all out, we have plus or minus 1, plus or minus 2, plus or minus 4. We have plus or minus 1/2. 2 over 2 we've already covered, so we're not going to do that. 4 over 2, we've already covered that as well. So then we go to 1 divided by 3, 2 divided by 3, 4 divided by 3, 1 divided by 6, 2 divided by 6, but we already have that covered. 4 divided by 6, we already have that covered as well in 2/3. So this is the list of all the possible zeros. Now, I'm going to throw in a kind of another bit of information we might possibly have. Maybe we have graphed it, looked on a graphing calculator, kind of seen some estimates of where the zeros are. In this case, we can rule out plus and minus 4 because there's nothing over here, nothing way over here. And if we look at this point right here looks to be around maybe 1/2. So we'll give 1/2 a try. Run it through the synthetic division, and we get a remainder of 0. So this is a factor. It's a root. And so we can take the results of it, and we started out with a quartic, x to the 4th, and so now these are x to the 3rd, x squared, x, and our constant term. And now let's go back to our kind of picture here. This kind of looks like maybe around 2/3. We do have a 2/3 in our list right here, so we'll take that 2/3, negative 2/3 that is, and put that into our synthetic division and another 0. And so then we have this down here as well. And we could factor out the 6, and we're left with this. And now that we're down to a quadratic, again, no need to keep trying all these. We have other ways of dealing with quadratics. And in this particular case, we're just going to use the quadratic formula. This isn't factorable, so the quadratic formula gives us some solutions at plus or minus 1 plus or minus root 3. So in the end, we get 4 zeros. 1/2, negative 2/3, 1 plus or minus 3. Okay. And this kind of leads to the irrational conjugate theorem. Let me just go back here. You notice how right here we had a 1 plus or minus root 3? The irrational conjugate theorem states the following. If we have a polynomial where all the coefficients are rational numbers, fractions, integers or fractions, if we find that a plus root b is one of the zeros, then its conjugate, a minus root b, also is. So a conjugate is the following. Here's an example. 1 plus root 5 is the conjugate with 1 plus minus root 5. If we had minus root 3, then we have positive root 3. These are conjugate pairs. These two are conjugate pairs. Okay, so let's do an example where we would write a polynomial function with the leading coefficient of 1, a root or 0 at 2, and another 0 at 3 plus root 7. Well, we could just take each one of these. X minus 2 would be a factor. X minus 3 root 7 would be another factor. But because we know that 3 plus root 7 is a factor, we know its conjugate 3 minus root 7 is also a factor. We're going to multiply this out, and I'll just multiply this term, and it becomes this over here. You see how I'm just multiplied x times x squared. I multiplied this term times this term here to get this right there. Multiplied this term over here by this term here to get this. And then I multiplied the two numbers. These are numbers. 3 plus root 7, 3 minus root 7 right here. As we expand this out, I use the distributive property right here. Minus 3 times 3, minus times here is negative 7. This negative 3, x right here. Negative times negative is a positive root 7x. Then with this, we're going to use a special property. I really hope you see that we have this kind of pattern, a minus b, a plus b. That should remind you of difference of perfect squares. So this turns into 3 times 3 squared minus root 7 squared, which is just 7. So we have 9 minus 7. These conveniently cancel away. We're left with minus 3x and minus 3x, that's minus 6x. We have 9 minus 2, that's 2. And now this orange, or this kind of orangish thing here, reduced kind of nicely down to this. So what we're going to do here is just multiply this all out, simplify it, and we get our polynomial that has a root at a root of 2. It has a root of 3 plus root 7, and also, of course, its conjugate. Okay, so, oops, you see one of the problems. You can work through these problems. I'll show the answer in 3, 2, 1. Okay, that's it for this lesson. Have a good day.